Okay, so the next one is reinforcement learning. This is a really exciting area, and this is one that I'm very excited about and I really like to play around with. And AI Studio uses a little bit of reinforcement learning because when it starts to solve a problem, next time it tries to do better and keeps doing better and better and better until it gets an optimal solution. So AI Studio becomes smarter over time. And so the Oracle, and it's actually not the AI Studio, the Oracle becomes smarter. So if you keep running AI Studio and solve the same problem, the Oracle over time gets better at solving it. It doesn't do it homogeneously, so sometimes you'll get a worse answer, sometimes you'll get a better answer, but it'll keep exploring this space and eventually it'll settle down onto, and I'll show you kind of like a value for AI Studio kind of after I've kept it running for a very long period of time and how it kind of converges. So it eventually does converge, but it could take a while. But if you keep running it, eventually you get the most optimal machine learning algorithm. So eventually it'll outstrip all humans. It's just how long you leave it running.
So that's per each different session
Yeah.
instance?
Yeah, every time you train a model, that kind of adds to its understanding. The Oracle understands. The Oracle improves on that.
I mean, if I made one model on the Oracle on AI Studio today,
Yeah.
and then so I did it again 2 weeks later, it would have gained experience from
Yes.
the first
Yeah.
time?
Yeah. As long as you didn't shut it down in between.
Oh, okay.
So we didn't save this. So unfortunately, we don't save the state if you shut it down. That's something down the line we'll be looking at. And the really cool thing is that we can build an oracle of oracles eventually. So which learns from all of the oracles in your network so that it basically learns how to solve all problems efficiently, which kind of becomes kind of Skynet-ish in a way. But that's not too unfeasible. We're not trying to invent Skynet, by the way. It happens accidentally. No. But yeah, the goal is that it learns how to solve problems more efficiently over time, and this is what we use in reinforcement learning. So it's basically optimizing a workflow. It's used for winning a game. And the game, for example, with AI Studio is winning at building the most efficient. It's a competition for building the most efficient neural network. And then increasing capacity, availability, robotics, it's used a lot. Autonomous vehicles, it's used in that space as well. Identifying context, weirdly enough, is used in that as well. So reinforcement learning was AlphaGo used reinforcement learning to win at Go. And it essentially uses, one of the cool ones is like there's, way back in the day I used to play on Atari. I used to have like an Atari system at home. And so it's kind of cool that they have something which basically always wins these Atari games. So it's kind of this effort I made into winning these games. It's like, So the principle is simple, but as always, the execution is not so simple. In fact, when I show you the loss function and everything corresponding to this, it is complex. But the principle is simple. So you have an agent, and you have the environment. And so the agent, in this case, for example, would be the Oracle. And what the Oracle is trying to do is its ability to solve the problem. So what the agent does is it acts on the environment and feeds back the current state of the system. So think about it from the Oracle's perspective. The Oracle is basically building a new set of, so for that problem, the Oracle builds a new architecture, identifies new hyperparameters. It'll act on the environment. The environment will then update and punish. If it has done better than the time before, it will update or reward the update. It will punish or reward the agent. So it'll tell the Oracle, you screwed up, improve, or it says, yeah, you did a great job, so it rewards the Oracle. And then it changes the state of the agent, which means that the Oracle changes so that it becomes better at its job. So So you've got many different aspects to this. The agent is what I talked about. The environment is what I talked about. Reward is the feedback from the system to talk about success or failure. The state is the current configuration of the agent with respect to the environment. So in this case, the environment for AI Studio would be for solving that particular problem, it would be maybe a combination of the hyperparameters, the architecture, the optimizations, and everything else that go into it. So these all represent values for it. And then the action is all the possible moves the agent can take, which is, again, I'm just using AI Studio, the Oracle as an example. The Oracle how it adjusts the hyperparameters and how it adjusts this is the most difficult part, and that's kind of proprietary. I won't talk about how it's done, but this basically, it's about how it makes adjustments to its understanding of the model and how it kind of changes the architecture, how does it do all these things. Then the policy is a function that maps the states to actions, which basically the state of the agent and kind of how that relates to a change in the behavior of the, like how do you translate the state of the previous state of the agent into the next stage. And then the discount is how much, so how much value does the agent place onto the future, which means as it starts to move forward and takes forward steps. So this is something we don't entirely do, simply because we don't want to eat up your computation time, because you want to minimize your costs, and we don't want to have the Oracle train on your time, basically, unless you really wanted to, in which case then if that's an ask, then we'll definitely do this. But basically this would be where it plays games with itself in a way and kind of figures out how it wants to value kind of future moves. And then it's the long-term return of the current state using whatever discount policy that it's applying to the future. And then you have, so think about it this way. It's and when you're doing an investment in something, you have a discount rate based on the ROI, basically, of that investment. So this is essentially what's going on there. So it's basically determining based on the discount of sort of the future steps, what is the ROI of that particular, of the current state of the system. So if the ROI is very high, then it will maintain that state. If the ROI is very low, then it will force the state to change. So it'll then make some fundamental changes. So pick a different investment in this case. And the action value is the long-term return of the current state using the discount policy and the current action. And trajectory is basically a sequence of action and states of the system, right? So here's this thing in action, how it would work. So time state 1, you have state S1, and there are only 2 possible actions that are possible in the system. So this is kind of a choose your own adventure. So you have 2 possible actions. So action 1 is taken, and it turns out that the system has been rewarded. And then it goes into a new state. And as a result of that, you now have 4 possible actions that can happen. So you start off, this is time step 2, it's now in a state 2, 4 possible actions. Action 3 is taken, and then the number of possible actions going forward is 1 possible action, and it's now in state 3. But action 3 was a bad choice, so it's now being given a -2 reward, which is a punishment. And then it kind of goes there, and so on and so on. In this case, again, it keeps making bad decisions. Action 1 was taken, and it has like a -1, so it's again a bad decision. But then number of actions is 5, and action 4 is taken and it's +3. So the aggregation of all of these moves is what you care about, because that's kind of like future looking and future discount looking. So then what it'll do is it'll try and maximize the reward profile for what it is assuming it's, so the eventual path that it's going to take. So, and that's how it wins, because it'll kind of like figure out all these different trajectories of rewards and actions and states to eventually get you the maximum return of that for that problem. And and in some cases, maybe making a bad move is okay because it opens up the possibility of, so in this case, maybe making a bad move was good because it opened up 5 possible opportunities, and so that it could actually get this +3 reward. So that's the cool thing about it, because it can make decisions based on, yeah, maybe I'll make a couple of bad moves now, but that opens up opportunities to make some really good moves later on. So that's really cool. I really love that. That's why I love it so much.
So as it progresses, does it remember the bad actions that were taken and not repeat?
So, the answer. So basically, what you're doing is it will converge onto those things. So what it'll eventually do is that as it starts to do this, it'll start to modify its policy, and its policy is basically the rewards taken into the future, and so it understands how to, yeah, it understands basically how to correct for mistakes that it's made in the past.
And so it does the same problem like over and over again.
Yes, yeah, exactly. So if you're training it to play Go, then you essentially run hundreds of simulations of Go until it learns how to consistently maximize its reward. So Go is a relatively simple example because there are only limited numbers of moves when you, well, there aren't a limited number of moves.
There are only 400 initial moves.
But there are, but that is so in this case it's actions equals 400. If there were an infinite number of moves, that would be a bad example. So long term, yes, over the duration of an entire game, it gets massively large, but that's okay. Reinforcement learning can take care of that, because at each step you have a limited number of moves. If you have an infinite number of moves, that's bad, because it means that it can't, it'll take a long time to learn anything. Well, it won't learn anything. Yeah, exactly. So
So you limit? Are there limits?
Yeah.
Just like there were date limits before.
Yeah, so you basically imply, the way you constrain the problem for reinforcement learning to have a finite set of possible outcomes for every move. And so with AI Studio, you have a much larger space. You have billions and billions of possible states that it can occupy. So, so how you kind of figure out the optimal move is a little bit more challenging. But the principle is the same. So what you're doing here is, this is your action value function. So what the action value, if you go back, just to remind you what an action value is. So the action is all state of possible moves an agent can make. And so the action value is basically figures out, so this is the policy, that given the state S, what is the probability of taking an action A. And what you're trying to do is figure out what is the best policy for rewards given this discount state gamma. So what you're doing is you're looking into the future and you're calculating this policy that will actually give you the best set of results. And notice that it's calculated S of A, so which means you're in state S, and you want to make an action A. And then based on that, what this will do is it will discount all future possible moves, and according to that policy pi. So the policy is like everything that you're going to do later on. The policy describes how you're going to change the state, or what set of actions are you going to make given the system state. So one of the things you do is you have sort of experience replays. And an experience replay, this is how it learns, is that you have an experience replay is you have a system that's starting at time t. It's at state S. It takes an action A. And then you get a reward t, and now it transforms into a system st plus 1. And so that experience replay forms a set in itself. So it's a fairly large set. And during learning, what we're going to do is we're updating, we're applying action value updates on mini batches within the experience replay. And then over time, we actually we determine the loss function. So this is exactly what we're doing there. So we're essentially taking all of the experience replays. So in which case, so you take mini batches from this massive set of all possible experience replays, and you take mini batches of that, and what you're trying to do is you're trying to minimize E. And the theta values are kind of the weights in your system, and that's how you adjust the weights. So, so what you're doing is looking at all the possible, like it's not every possible, but you're looking at a huge set of possible experience replays. And based on those experience replays, to calculate your loss function, is that you look at, firstly, what are the optimal values of pi that would take you through that. And then the second is you're going to be looking at, and what you're going to do is your values of theta are essentially like the weights in your system that continuously get updated. So you're looking at changes in value of reward function and the weights in the system, and that will actually get you the loss, and that back propagates into the system. So it's still, you're still employing the concept of back propagation. Right. And so that is kind of what AI Studio would, so running one simulation of that, so in terms of how it converges. So the training epochs in this case is how many times you've actually run a model. So when you get to about 80, you see it starting to stabilize. So around 40 times building the model, you're still kind of, and then it starts to stabilize around 80 to 100. The last thing I want to talk about before we move on to AI Studio is GAN. So GAN is the base. There's a lot of math behind it, so I'm not going to go into that. But the basic concept is very simple. So think about, you have a counterfeiter and you have a expert, like a detective. So a counterfeiter is producing currency, and he's kind of like generating currency, and the detective is there to basically determine whether it's real or not. And so initially, when the counterfeiter starts, the detective consistently is able to say that, no, this is not real currency. But as the counterfeiter gets feedback, the counterfeiter will change his design, and it'll improve. And eventually, when the detective, it's 50-50, so he's basically just guessing, it's almost like a random guess. When you get to that point, then you know that the counterfeiter is pretty good. It's very close to getting to the optimal value. So the generator takes a random input data, and from the random input data, it'll kind of assemble that into some kind of structure. Initially, it's completely off. It'll be like you have no idea what it'll be just bizarre. So it'll pass so the discriminator is, so let me start with the discriminator. The discriminator is just a simple classification model, which is it learns what a dog looks like, or it learns what human face looks like, or whatever. So the discriminator learns how to tell that something is a face, or a dog, or a hot dog, or whatever, right? So that's what the discriminator learns how to do. So that's all it is. So then the next thing is that you build a generator, and the generator will essentially assemble all of these things together and will pass that data to the discriminator, and the discriminator says, well, it'll do a simple classification, and it says, well, based on what you've given me, I decide that this is not a hot dog. And then it'll go back and tell the generator, this is not a hot dog. And so then the generator will then try again, will produce another hot dog, attempt at making a hot dog, and then goes back, and it's a cyclical process, and eventually the generator will consistently generate hot dogs. And so, for example, you can have it generate new types of music in the style of Mozart, and you can generate new types of, so if I train and generate, so I have a discriminator, for example, that can tell whether a chemical is carcinogenic or not. This is a very bad example because that's what terrorists could do. But for example, if I have a discriminator that can tell whether something is carcinogenic or not, and I have a generator that is able to generate molecules, then it'll keep submitting new molecules into this, and eventually it will say, no, this is carcinogenic. And so then you know that that molecule is carcinogenic. So, or let's be positive, it's non-carcinogenic. So, but the other, I mean, this can be used in a lot of things, like curing cancer, well, not curing cancer, but curing, maybe like figuring out a new drug to lower cholesterol rates, and you figuring out a way to maybe reduce heart problems and so on. So with the molecular stuff that we're doing, the generator will consistently produce new types of molecules that would, that eventually the discriminator can't really tell it apart from drugs that reduce cholesterol. So which means when you hit that point, then chances are what you've just generated can reduce cholesterol. And then with drug safety, you can actually look at whether something's toxic or not. So you can train a discriminator into, like, what does a toxic chemical look like, and then have a and so think about it this way. So when you, for example, you have a generator that generates anti-cholesterol drugs, but some percentage of them will probably be toxic. So then what you do then is you run it through another classification model, and it will then say, well, these drugs are toxic, these are not. So you can reduce animal testing, which is one of the things I think would be a really laudable goal behind this. I would like to see an end to that, but but yeah. So that's roughly how GANs work. Cool. So this is part of the more exciting some of the more exciting areas of machine learning right now. There's some other things which we're going to be implementing not too far from now, which would be automatically identifying the most some of the key features like automatically detecting key features and things like that. So that's going to be a future version of AI Studio.